The next topic is topic 8.3, the particle zoo. From this name itself, you can understand what this topic is about. It's about the different types of particles. For example, if you go to a zoo, you will get different types of animals. Similarly, here you will have the different types of particles. So again, before we start this, make sure you are familiar with the mathematics that you will need. We have different types of particles. You would have seen the names of some of these particles: quarks, neutron. So let's start with chapter 8.3, part 1, particle interactions. By the end of this section, you should be able to use the equation E equals mc squared. Now again, you would have seen this equation, but here delta E, the change in energy, is equal to c squared. That is the speed of you would have, again, like I said, you would have seen this letter C. We used it in V equals F lambda, where we changed V to C. C equals F lambda, where C was the speed of light in vacuum. Then delta M means the change in mass. Now here you will see that the mass can convert to energy and energy can convert to mass. We will see some reactions also. For example, if a positron, that is a beta plus particle, and an electron comes together, you will have annihilation, where the particles will become energy. I will show you one example right now. Yeah, so here I am using the Cambridge textbook. You can see it right here. This is the electron and this is the positron. Positron is the antiparticle of electron. Antiparticle basically has the same mass but opposite charge. When these two come together, they annihilate. Energy is released in the annihilation of matter and antimatter. So this is matter and this is the antimatter. What happens? It becomes gamma ray photons. Now you know gamma rays don't have a mass. So what happened here was annihilation. It became energy. The mass became energy. This has a mass. You know, electron has a mass. Positron also has a mass. But what happened in the end? It became energy. So there are some details over here about this. Positrons are a form of antimatter. When a positron collides with an electron, they annihilate each other. Their mass is converted into electromagnetic energy in the form of two gamma ray photons. You can see here one, here's another one. See, two of them. Energy is released in the annihilation of matter and antimatter. So now you know what is matter and antimatter. And here you can see some details. Figure 16.4 shows the basic characteristics of the different types of radiation. Their masses are given relative to the mass of a proton. Charge is measured in units of E, and you know E is the elementary charge. It's also given in your data sheet in the past exam papers, in your exam papers. So these are important. Now we will go back to where we were. Then use and convert between mega electron volts, giga electron volts, and mega electron volt divided by c squared, or giga electron volt divided by c squared. Now this electron volt is a unit of energy. If you remember the equation, W equals Q times V. So let me show you that. I think in a previous lesson also I explained it. Yeah, so last time we saw this. This is where we can convert from electron volts to joules, or from joules to electron volts. So for example, 1 electron volt is 1 times E times V. And we saw this equation, V equals W over Q. When you learnt the definition of voltage or potential difference or even EMF, you would have seen this equation. V equals W over Q. Work done divided by charge moved. So volt is joule per coulomb. Then we have the quantities here. V equals W over Q. Then W equals VQ. Now if you compare this with this, you can see that V is there. Then Q is the charge, E. So 1 electron volt is equal to 1 times E times V. And E has a numerical value. I told you it's also in your data sheet, and you have seen this previously. It is the elementary charge of a proton, magnitude of charge of a proton or electron, 1.6 into 10 to the power minus 19 coulomb. So we can also write this as 1 times E times V. 1 times E, the value of E is 1.6 into 10 to the power minus 19 coulombs, that is this, then times V, see, times the V, and now we have converted 1 electron volt to joule. Now coulombs volt is joule. Here I have written the unit of this is joule, work or energy is joule, then this is in unit of voltage is volts, unit of charge is coulomb. So joule is volt times coulomb. That is what we have here. So let's see. Okay, so what we will have is that unit electron volt. It can be mega electron volts or giga, and mega are metric prefixes. Mega is a million, 10 to the power 6. Giga is a billion, 10 to the power 9. So we can have in giga or mega electron volts. Then divide by c squared. So you can see this here is divided by that. So we will see the details later. Okay, so you can see the word annihilation here, and you can also see the electron volts. I basically discussed this part, but we will go through some details, and that's all we have for this particular lesson. So here you can see the electron volt is the amount of energy an electron gains by passing through a voltage of 1 volt. If you look at this, you can try to understand that. So 1 electron volt, if you have an electron and if you accelerate it through a potential difference of 1 volt, it will gain this much energy. So like I said, let's say imagine you have two parallel plates, okay, and the potential difference between those two parallel plates is, let's say, 1 volt, okay, and let's say this side is the negatively charged plate and this side is, this plate is the positively charged plate. 3 4 5 3 4 5. Okay, so you have a uniform electric field. Now if there is an electron here and let's say it is at rest, when you release it, what will happen? It will get accelerated. Why? Because this side is negatively charged, negative and negative repel, and the other plate is positively charged, so it will attract this. And also you have learned that the electric field lines are always going from the positive plate towards the negative plate. So here I can draw the electric field lines, and they are always perpendicular to the plate or the surface. So in this case you can see the angle here will be 90 degrees. Now what will happen is this electron will be attracted to this side, so always the electron moves opposite to the direction of the electric field line, or it will move along a tangent to the electric field line. Now in the beginning the electron is at rest. Once it comes here, it has gained energy. So how much energy it has gained is 1 electron volt. When it is here, the amount of kinetic energy it has is this much, 1, because it has a charge this much, and then there is a potential difference. As a result, its speed will increase. So once it comes here, it has gained energy. How did it gain energy? It was due to the potential difference between the plates. So you can now try to understand this definition, and here you can see the conversion factor is also given, 1 electron volt. What I've written here, 1 is equal to 1.6 into 10 to the power minus 19 joule. The electron volt is the amount of energy an electron gains by passing through a voltage of 1 volt. So once you know this you can figure out. 1 mega electron volt means mega is a million. So 1 times 10 to the power 6 times the electron volt. So simply you multiply this by 10 to the power 6. Now 1.6 into 10 to the power minus 19 into 10 to the power 6 is minus 19 plus 6. You add the powers. Remember rules of indices. So you get 10 to the power minus 13 joules. Okay, so then annihilation, remember we saw earlier, is the phenomena in which a particle and its antiparticle equivalent are both destroyed simultaneously. That means at the same time in a conversion into energy. So you see, mass became energy, which is carried away by force carrier particles such as photons. So a nice diagram was given here. You got 2 gamma photons when an electron and its antiparticle, the positron, came together or collided. Positron collides when an electron, they annihilate each other. Okay, so then pair production. Now the reverse can also happen, is the phenomena in which a particle and its antimatter equivalent are both created simultaneously in a conversion from energy. So if this can happen, the reverse can also happen. You can get these two forming, these two gamma ray photons, they can form the electron and positron pair. That is called pair production. So basically these are the key definitions. You should know them very well, because in the exam papers they can ask you. So make sure you memorize these definitions with understanding. Now let's go back to the details of this lesson. I have anyway already given you some details, so let's go through whatever is here. Now this part is basically some history from some religious books. I think in the beginning God created the heaven and the earth. This is the first verse in the Bible, in Genesis chapter 1 verse 1. This is the first line of the Christian holy book, the Bible. So about creation, even the religious books say something about it. In Buddhism there is something called the Aganya Sutra. In that also you have something about the Big Bang theory, that the universe is expanding. So the creation story of the indigenous people of Australia claim that everything was created from the dreams of their distant ancestors. So Hinduism has several accounts of creation, one being that everything was magically created by Brahma under instruction of Vishnu, who had just awakened from dreaming by the primordial sound. Okay, so those students who have learned Hinduism may be familiar with this. Some Native Americans hold to the idea that Earth Maker wished for the earth and it was formed. The implication from most creation stories is that from nothing the material of the earth was brought into being by an unexplained theory, unexplained entity. So let's say the universe was created from nothing, something like that. Some scientists take such apparently supernatural whimsy as strong evidence that religion is fanciful nonsense. However, one of Einstein's most important theories seemingly suggests exactly this. Matter can appear where previously there was nothing but energy. So I gave you some example here, but actually it's not from nothing. You have this, and then from this only you get the other one, or from this you get this. So it's from energy you get the mass, or from mass you get the energy. That is where we have this Einstein's equal mc squared equation. So we will see. However, one of Einstein's most important theories seemingly suggests exactly this. Matter can appear where previously there was nothing but energy. Matter and energy are regularly interchanged in the universe according to his well-known equation. So again you can see matter and energy. See also here, see here, this is energy, here you have matter. Matter can appear where previously there was nothing but energy. Matter and energy are regularly interchanged in the universe according to his well-known equation E equals mc squared. In this equation, multiplying the mass of an object by the square of the speed of light gives the equivalent amount of energy. Given a suitable quantity of energy, such as that in a gamma ray photon, particles can spontaneously appear and the energy disappeared from existence. So that is what you have here. So suddenly you get this and you don't have the gamma ray photons anymore. So this equation is important. Given a suitable quantity of energy, such as that in a gamma ray photon, particles can spontaneously appear, suddenly appear, and the energy disappears from existence. This is so commonplace in the universe that it should not surprise us. The reason it does is that these events only happen on a subatomic scale. So you can see it happens at a subatomic scale. Now you don't have a human suddenly disappearing. So this happens at a subatomic scale. You don't have a car at once disappearing into thin air. But this can happen at the subatomic level. So we cannot detect them without complex machinery. Okay. So here is a worked example. A gamma ray photon converts into an electron and a positron, an anti-electron, that is the positron, that has identical mass to the electron. Now again we can refer to the same diagram again and again. It's referring to what I was explaining earlier. So you have the electron and its antiparticle, which is the positron. So like I said before, they have the same mass but opposite charge. An anti-electron, that is the positron, that has an identical mass to the electron. Calculate the frequency of the gamma ray photon. So remember, from this you get this. We are supposed to find the frequency of the gamma photon. So we can use this equation. Now remember, E equals mc squared or delta E, the change in energy, or that amount of energy is equal to the change in the mass. So remember, you have mass in the beginning and then you have no mass. So what happened? The mass converted to energy. So mass of an electron, it's given in the data sheet also, is 9.11 into 10 to the power minus 31 kilograms. You don't need to memorize this value as it is given to you, but when you do a lot of questions, you will automatically remember the mass of the electron, the charge of an electron, like that. So c is the speed of light in vacuum. That is also given, but like I said, you should know it, because when you do a lot of questions you will remember it. But this, like I said, it's better, you should know the value of the speed of light in vacuum, which is 3 into 10 to the power 8 meters per second. So remember, c squared times the mass. Okay, so we have 9.1 into this. This is the amount of energy needed to produce an electron or a positron. To produce both the energy of the photon must double this. So you can see now this we have doubled it. Now again, this is the amount of energy needed to produce an electron or a positron. So to produce both, the energy of the photon must be double this. Now again, if you look at this diagram, you can see it's not just one. You get two gamma ray photons, and also you have two particles here, the electron and the positron. So in the equation itself, we can multiply this mass by 2 and write it, and we will get the answer 16.4 into 10 to the power minus 14 joules directly. Now once we have this, we can use the equation E equals hf. You would have seen this, E equals hc over lambda, because f is equal to remember, V equals f lambda or C equals f lambda. So you have also E equals h c over lambda, because f is equal to c over lambda, or we can say c equals f lambda. Now then we can find the frequency. So we know the energy, and we know that this is h is the Planck's constant. Okay, that is also a constant. It's given in your data sheet, but like I said, when you do a number of questions, you will automatically remember this. Then you get the answer 2.47 into 10 to the power 20 hertz. This reaction is known as electron-positron pair production. Now you can see, if you go back to the definition, you can see that this reaction is known as electron-positron pair production. See, a gamma ray photon converts into an electron and a positron. Calculate the frequency of the gamma photon. So basically what we saw here is the reverse of this. So here what is happening, the arrow is this way, but in this question the gamma ray photons get together and form the electron and the positron. That is what we call electron-positron pair production. In momentum terms, it is just like an explosion. Initially only the photon existed, so there was some linear momentum along this initial direction. Their components of momentum must sum to the same total as the photon had. Perpendicular to the initial momentum, the electron and the positron produced must have equal and opposite components of momentum. Actually, plural of momentum is momenta, momentums, so that in this direction it will still total 0 afterwards. So if you see this diagram here, once it is produced, they should be traveling in opposite directions, so that the total momentum before is equal to the total momentum after. So in an explosion, the total momentum before the explosion, you can say, it has to be equal to the total momentum after the explosion. So before an explosion, what happens? Nothing is moving, and suddenly things start moving apart. So total momentum before explosion is equal to 0, because all the particles are stationary. That means total momentum after should also be equal to 0 because of the principle of conservation of momentum, or law of conservation of momentum, which states that total momentum before an interaction, explosion, collision, all mean the same thing when we say the word interaction. So total momentum before should be equal to total momentum after. That means when this happens, because in the beginning the total momentum is 0, always if it's an explosion, we can say we can assume like the things are stationary, and then suddenly things move apart. So that's what is explained in a way here. Along this initial direction, their components of momentum are summed to the same total as the photon had, perpendicular to the initial momentum. The electron and positron must have equal and opposite components of momentums, so that in this direction it will still total 0 afterwards. Again, if you look at this diagram, so the total momentum here, because they are traveling in opposite directions. Remember, momentum is a vector quantity. So mass of this times the velocity of this way will be equal to the mass of this times the velocity of this way. That is the magnitude. But remember, since momentum is a vector quantity, when you add them, it will equal 0. Because here the velocity is this way, here the velocity other way, opposite direction, 180 degrees opposite. So when you total, the momentum will be 0. Same thing here. Okay, in any reaction, the total combination of matter energy must be conserved. If we add the energy equivalent of all matter particles with the energies before and after the reaction, the numbers must be equal. So that's what we have here. Whatever decrease in mass is equivalent to the increase in energy. So that's what is explained here. So you can see the total combination of matter energy must be conserved. That means total matter plus the energy before should be equal to the total matter plus the energy after. That is what we say it's conserved. Now, for example, when you learn about conservation of energy, conservation of momentum, or some other, when we hear the word conservation, that means total before should be equal to total after the reaction, or before the interaction should be equal before and after. If we add the energy equivalent of all particles with the energies before and after the reaction, the numbers must be equal. Okay, it should be, I think here, mass, right? Energy equivalent of particles with the mass equivalent before and after the reaction, it should be same. Okay, then we have annihilation. Now again, this is an example of annihilation, this forward reaction. Okay, from here to here, see, this reaction is annihilation. Annihilation, why? Because the particles get together and you don't get any particles afterwards, instead you get energy. So the definition was also given here. Annihilation is the phenomenon in which a particle and its antimatter equivalent are both destroyed simultaneously in a conversion into energy, which is carried away by force carrier particles such as photons. So let's go back here. Annihilation: just as a matter can appear spontaneously through a conversion from energy, so just as matter can appear spontaneously through a conversion from energy, that is what we saw in this example here. Matter appeared from energy. Just as matter can appear spontaneously through a conversion from energy, so energy can appear through the disappearance of mass. So again, referring to the same diagram, energy can appear from the disappearance of mass. So energy can appear through the disappearance of mass. This is the source of energy in nuclear fission and fusion. You have learned the nuclear fission and fusion reactions. Even in the IGCSE or O-level classes, you learned the nuclear fission reactions. Remember, you have a nucleus, for example uranium, and neutrons are directed at it. So the neutron is absorbed by the nucleus becomes unstable and it disintegrates, it breaks. That is nuclear fission. Fission means like breaking. Then also you learn nuclear fusion. In nuclear fusion, what happens? Nuclei, for example hydrogen nuclei, fuse or get together to form a helium nucleus. These are the reactions that occur in stars such as the sun. Hydrogen nuclei fuse to form helium nuclei. That is an example of nuclear fusion. Okay, so this is the source of energy in nuclear fission and fusion. In both reactions, the sum of the masses of all matter involved before the reaction is greater than the sum of all mass afterwards. Now why? Because mass afterwards is less, because some mass was converted to energy. So here again, if you go through this carefully, you can see the mass before is greater than the mass after the reaction. Why? Because some of the mass was converted to energy. So in both nuclear fission and nuclear fusion reactions, we get energy. Okay, so nuclear fission reactions take place in the nuclear power plants, nuclear power stations. In this world there are nuclear power stations, so there nuclear fission takes place, and that is a power station, so we get energy from there. Now in the sun or other stars, you have nuclear fusion reactions, and we get energy from the sun. Sun is example of a star. So both the nuclear fission and fusion reactions give energy. Now where did this energy come from? Because of annihilation. Because matter and antimatter get together and annihilate, we get energy. For example, gamma ray photons we saw over here. Okay, now I think that is clear. This mass difference is converted into energy. See section 10.1.3. Now we are in section 8. We'll have a quick peek at this section also right now. Okay, so chapter 10.1.3 is about fission and fusion. So for more details you can go through this part, but also I explained briefly just now. Let's go back. Okay, so we are back here. In a nuclear power station, we extract this energy as heat and use it to drive turbines to generate electricity. So for more details you can go through the nuclear power station. I think we looked at 10.1.1, right? This is 10.1.3. All right, we looked at the correct one. It's 10.1.3 that we looked at, not 10.1.1. If a particle and its antiparticle meet, antiparticles are the antimatter version of regular particles. So that is in the next section, 8.3.2. We are in 8.3.1, but we can have a quick glance at 8.3.2. Here you can see we will go into the details. Also in my notes I have the particles and the antiparticles. We can see those details there. Here actually they have not really given, right? 8.3.2. Okay, let's finish this off. Antiparticles are the antimatter versions of regular particles. Okay, so here I'm showing it from the notes now. You can see this is the antiparticle. In this third column has the antiparticles of these particles. For example, electron, the antiparticle is the positron. It has the same mass but opposite charge. And similarly you can see here, you would have heard these words, electron, neutrino. When it came to beta decay, you had this, the electron neutrino and the electron anti-neutrino. We will see again these reactions afterwards. It's there in the next 8.3.3 I think. So here you can see we use a bar on top also. See, we use a bar, or we use the charge opposite sign like this. So here you have the particle, the antiparticle, muon, then the antiparticle of muon, like that. So this, remember, is the electron antineutrino. Similarly here this is the muon antineutrino, this is the tau antineutrino, this is the tau neutrino, this is the muon neutrino, this is the electron antineutrino. So the first three columns here are important. Let's go back. Yes, so if a particle and its antiparticle meet, they will spontaneously vanish from existence to be replaced by the equivalent energy. We call this interaction annihilation. Okay, now you know what annihilation is. This reaction was supposedly the main power source to drive the Starship Enterprise in the science fiction series Star Trek, Figure A. So if you have watched this movie, you might know science fiction series, Star Trek. The fictional starship Enterprise was said to be powered by a matter-antimatter annihilation reaction. It is not commonly suggested that the annihilation reactors could be used as a power source on Earth, as antimatter exists so rarely. Also, if we could find a supply of antimatter, it would annihilate or contact with any matter, which would most likely be before it reached the reaction chamber we had to set up to extract the energy for conversion into electricity. Okay, so far it's not a feasible way to get energy. Alright, then electron volt units. We have seen in book 1 section 3.1.2 the electron volt as a unit for very small amounts of energy. Remember that 1 electron volt is the amount of energy gained by an electron when it is accelerated through a potential difference of 1 volt. I already explained it here in the beginning today of this video. This is equivalent to 1.6 into 10 to the power minus 19 joules. So you can see 1 electron volt is this many, 1.6 into 10 to the power minus 19 joules. So it is a very small amount of energy. You can see this is a very small number. Even in particle physics terms, it is common for particles to have millions or even billions of electron volts. For this reason, we often use mega electron volts or giga electron volts. I told you mega is 10 to the power 6 or a million. Giga is 10 to the power 9, which is a billion. We often use mega electron volts or giga electron volts as units of energy in particle interactions. Similarly, the atomic mass unit U is not an SI unit but is commonly used in particle interactions, as it is often easier to get to grips with 1 U equals 1.67 into 10 to the power minus 27 kilograms. Again, in your data sheet, I think this is given. So you can look at your data sheet. You will see these conversion factors. So similar to this, you can see we have this. This is 1 U is not atomic mass unit, that is U is not a SI unit but is commonly used in particle interactions and is often easy to get to grips with this. As we know that energy and mass are connected by the equation delta E equals C squared delta M or equals mc squared, we can also have mass units which are measures of this divided by this. See, E divided by C squared, such as mega electron volts over C squared and giga electron volts over C squared. 1 U of mass is equivalent to about 931.5 mega electron volts per C squared. Okay, so let's go through an example to help you understand this better. Calculate the mass in kilograms of 1 mega electron volt per C squared. So again, very simple. Like I said, if you use this method by knowing that the sign between the number and the letter and the two letters is a multiplication sign and substitute the numerical value of the letter, then you can directly convert it to joules here, for example. Same way you can try this. So let's do that here. 1 into M into E into V. The sign between the letters and the numbers and the letters is a multiplication sign. So it's 1 times M times E. M is 1 million, which is 10 to the power 6. So we will write the numerical value of M here. Then again the sign between E and M is multiplication, that is this you see here. Then E is having the numerical value, that is the elementary charge, 1.6 into 10 to the power minus 19 coulombs. Okay, so coulomb volt is what? Joule. So once you multiply this, you will get this, but they haven't written that unit. However, in my explanation, I have shown you once you substitute the numerical value of E, which has the unit coulomb, coulomb times volt is joule. See, the conversion is shown here as well. Okay, so now you know how to convert from mega electron volts to joules. Very simple. If you know this method, you can apply it here or even for other questions. Let's see, in SI units, C, that is the speed of light in vacuum, is 3 into 10 to the power 8 meters per second. Now you have, remember, we completed the numerator of this fraction, but what about the denominator? So let's convert the denominator and we'll use the value, numerical value for the denominator and get the final answer in kilograms. Okay, so 1 mega electron volt over c squared, that is what we need to convert or get in the unit kilograms. Now based on this equation, you can see delta E divided by c squared is equal to delta m. So that means delta E, the energy divided by the speed, the joule divided by meters per second, should give you kilograms. Okay, so once you have everything in SI units here, your final answer will also be in SI units. SI unit of mass is kilograms. Let's do that. Now the numerator we already did here, so we'll write that here. Then the denominator is the speed of light in vacuum squared. Already this is in SI units, so everything here is in SI units, which will give the final answer in SI units. Therefore 1 mega electron volt divided by c squared is equal to 1.78 into 10 to the power minus 30 kilograms. This is about twice the mass of an electron. Okay, learning tip: no particle interactions can occur if they violate any of these conservation rules. I have already told you, always the momentum is conserved. That conserved means total momentum before equals total momentum after. So that's what the word conserve means. Conserve means whatever is total before should be equal to whatever you have, the same thing total after. Same thing applies to mass, energy and also charge. There are other rules that must be obeyed, but these three are critical as all particles involved will have some of each property. Okay, so then there are some questions here. Make sure you answer these questions to ensure that you have a better understanding of what you learned in this lesson. And also I went through the definitions. I told you that these definitions are important, so make sure you do all these questions and check the answers in the answer script. This is the end of the chapter 8.3.1. Next we will see the particles, so which is chapter 8.3.2.